Hi, welcome to our presentation on the Unity's cloth component. My name is Donovan, and my team members are Zheng Kwang and Dixon. So I'll be covering the theory side of cloth, and Zheng Kwang will be covering the Unity implementation of cloth, and Dixon lastly will be covering the case study of it. So to give a short overview about what cloth mechanics is, they offer dynamic visual elements and they increase immersive experience as the player is playing in the virtual world. And this can be found in games such as Assassin's Creed, The Legend of Zelda, Breath of the Wild, and in these games you can find realistic movement of different cloth behaviors that is influenced by physics. While creating cloth simulation in games, this will actually be very challenging because you have to make it dynamic and realistic at the same time, replicating an actual behavior of a cloth that can be found in real life. And in order to do this in a virtual world, you have to consider many different calculations of physics, wind dynamics, and environmental interactions, and not to forget the player's movement. Let's say, for example, making a cape, and while considering all these factors, at the end of the day, your game still has to be at top performance and it has to be smooth. And with that in mind, I'll start off with talking about the theory of the cloth. Starting off with an introduction to cloth and the baseline of it, which is called textiles. These textiles are designed and manufactured in factories to create woven fabrics, and these woven fabrics are then used to create our shirts and jeans, jackets that we are all wearing outside today. And in order to create these woven fabrics mechanics are taken into consideration. There are theories called fabric anisotropy, stress-strain relationships, and while also considering different properties of the textiles, such as the tensile, bending, and shear properties, and the structure of yarns. So when talking about the importance of realistic cloth simulation, we will then have to talk about different uses of it in different industry. Firstly, we have virtual rating technology, and this is mostly used in e-commerce and to help with computer-aided design in clothing, as well as film and game production. And in order to have great user experience, it has to be visually appealing, and in order to achieve that, you have to have realism and speedy simulation in such cloth simulation. Second example can be found in films, animations, and movies. And different movies, different companies have their own simulation techniques for cloth. So the first example is Disney's Frozen, and they have their own custom-built cloth simulation system called Tonic. And with this simulation system, they can create snow accumulation, wind interaction, and ice transformation. There are also two other movies and two other different simulation techniques. And with these different simulation techniques, realistic, fluid, and dynamic effects can be incorporated in such movies. Moving on to different uses of cloth. Cloth can be used to create character clothings, game objects. So as for character clothing, you have capes and costumes, and also cloaks that can be used for characters. And for game objects, you have flag and banners that can be found in game as well. And all these game objects and clothing have to respond dynamically to movement and other external factors. This is because we want to add flow and realism to the game and the simulation, which will be more visually appealing. So when talking about external factors or forces, if we talk about all three Newton's laws that come into play, so the first law of inertia, the cloth maintains its state of motion until an external force like gravity or wind interacts with it. And let's just say if there's an interaction, we come to the second law, which is force equals mass times acceleration, and this will lead to acceleration based on the cloth's mass. And third law, which is action and reaction, this comes into play with if the cloth interacts with obstacles or surfaces, leading to reaction and subsequent behaviors. Next up, I'll be talking about cloth dynamics. There are different methods of cloth simulation. The first three you can see is particle and physics-based simulation, Verlet integration, mesh spring damper model, and other types of simulations such as elastic base and geometry techniques are mainly used in Maya and Blender. So when talking about particle physics-based simulation, we have to talk about position-based dynamics. And this method is used to simulate cloth based on its position, vertices, and constraints. So how it works is, initially you retrieve the position of the cloth mesh vertices. Next, it will try to predict a new position for the vertices. And this depends on whether there's any external forces being applied to it, or in any case, if there is velocity being applied to it. And by going in a loop, this updates the cloth mesh vertices continuously. And this is based on the predicted new position and conditions of different constraints. So the different constraints to account for is distance constraint, bending, and collision constraint. So for distance constraint, it is mainly used for maintaining distance, the original distance between each vertices. And this is to prevent stretching and compression. Second is bending constraint. This is to increase resistance to bending or the folding of the cloth. So the third constraint, which is collision constraint, is to handle collision between the cloth and other objects. So to summarize how PBD works, it works in a way where it calculates new predicted position for the cloth vertices while mainly fulfilling the constraint conditions so that the cloth is intact. So if let's say there's a collision, the cloth has to respond to these collisions. There are two types of collision. First is self-collision and second is intercollision. And how this cloth responds to this collision is to either fold, drap, or slide off surfaces. So as for self-collision, is to stop the cloth from penetrating itself, and intercollision is to allow collision with other objects. So the algorithm used to calculate collision and response is node spear distance. So an example I can give is, let's just say the cloth is in collision with a 3D sphere game object. So PO here is the O position of where the cloth particle or vertex is at. P prime here is the intersection point of the cloth and the sphere. And P1 here is the predicted new position, which is the point of collision. O here is the center of the sphere object. So if we compare the distance between P prime and O, and if it's shorter than the radius of the sphere, this means that there's an intersection, which shows that there's a collision. So in order to calculate the collision point, which is P1, we have to take O plus the normalized vector, which is the distance between the original point and the center of the sphere, times the radius plus the offset. The new velocity has to be calculated as well, which is to use a normalized vector, which is the distance between the original point and the sphere, the center of the sphere, plus the normalized vector, the original vector. And this is so that you don't want the cloth to just be collided and stuck there. You want the cloth to be collided and respond, so it will bounce off, it will drip around the sphere game object, and so on and so forth. So the second simulation is quite similar to PBD, and it's called Verlet integration. It's a numerical method, and why it's useful is because it's stable, it's simple, and it suits with preserving the different constraint conditions. So it works similarly with PBD in a way where it uses the distance between the current and the original position, and with that value it predicts the next position by using the current position of the cloth mesh particles and the distance between the current and the previous position of the cloth mesh particles. This is the formula used to calculate Verlet integration, which is to predict the next position of the particle. So RT here is the current position of the particle at time t, and H here in this case is a time step. So RT minus H here is the previous position of the particle, and RT plus H here is the next position of the particle as the time is increasing. So AT here is the acceleration of the particle at time t, and F is the force that's acting on the particles. So it can be gravity, it can be wind, or it can be another external force. And M here is the mass of the particles. And this is how Newton's second law is coming into play here. So with this formula here, this is the original formula, and let's just say if there's an external force coming into play, you can substitute the acceleration here by doing a F divided by M, force divided by the mass of the particles, and this can be used to predict the next position of the particle as the time is increasing. So moving on to external factors with gravity, which we all know is to simulate cloth falling down in this case. And in order to do that, we have the formula for it, which is F equals to mg. M in this case, which is the mass of each of the particles, and g is the acceleration due to gravity, which translates to gravitational strength. Second is, let's just say there's an obstacle, right? A ball being thrown at a cloth. Right? The collision and the force of the ball has to be taken into account of. So another factor is wind, and this is used for the flattening of the cloth, deformation of it maybe if you want it, and also directional movement. And let's say if the wind is blowing on one side. So A here is the maximum strength of the force, V here is the frequency of it, and T here is at the current time, right, at a specific point in time. So why cosine is because you want the wind force to be blown in the same direction, but you want it to be blown at the cloth at a time interval, so that it wouldn't be a constant blowing where the cloth would just be being affected by the wind force, maybe like a tangent graph. But then we use a cosine here because we want the cloth to be blown and then stop and then blow and stop and subsequently. This is so that you'll be more realistic. So the difference between both algorithms, PBD, position-based dynamics, and Verlet integration, is that PBD focuses more on constraint conditions, so to fulfill the constraint. This is so that the cloth is still intact based on the settings of the constraint as well. And the main method that they choose to implement is to maintain the distance and angle between each vertices. However, for Verlet integration, it updates the position accurately based on the difference in the current and the opposition of the particles. So instead of saying, oh, you can only use one algorithm, I would like to say that you can combine both algorithms so that both of them work hand in hand together, where one focuses on fulfilling the constraint condition while the other updates the position accurately. So the last simulation method is mass spring model, and we have to talk about masses and springs. So masses here are the particles that make up the cloth. So if there are more particles, means there are more collision stability. Springs here in this case are here to hold the particles together in the cloth, while also preserving the constraint configuration. And these springs here have to obey something called the Hooke's law. So the Hooke's law formula is F equals to minus K times X. F here in this case is the force that's being exerted by the spring, and minus K here in this case is the spring's stiffness. And X here in this case is the displacement of the spring's length of its rest position. So with this formula here, it can be used to simulate the cloth smoothly by calculating the force that's being applied on it, so that the particles will move subsequently based on the force that's being applied. And hence, I've come to the end of my presentation on the theory part of cloth. In order to have a very, very realistic and smooth cloth simulation, there has to be a combination of different simulation techniques and algorithms. Not to forget physics calculation and the application of Newton's laws and external factors such as gravity and wind. And all these guiding framework are very, very crucial. And I would like to say thank you for your time, and moving on to the next person.
Okay, I'm Zheng Kwang, and I'm gonna present my part, which is the Unity implementation overview. Okay, so firstly, what is Unity's cloth component? So it's Unity's inbuilt feature, and it simulates realistic cloth fabric-like physics. So bending stiffness, it just refers to how resistant the cloth is to bending or flexing. Stretching stiffness governs how resistant the cloth is to stretching. Damping in cloth simulation helps control the dissipation of energy, and the constraints are like rules or limits applied to the movement of cloth particles, and surf collision prevents different parts of the cloth from intersecting or passing through each other. So why is it important to have realistic cloth behavior environment? So um, cloth realistic cloth behavior gives a very appealing and realistic look to the game, and makes the user immerse more with the game. And also cloth can interact with in-game mechanics such as different cloth related clothes have different effects on players, so on and so forth. Okay, so this is the user interaction of the cloth component, so what the user can change in the cloth component. So as previously mentioned about the stretching and bending stiffness, you actually can change it over here between a range of 0 to 1, 1 being the most stiff, and you are changing it according to your purpose. You also can change the damping settings. So increasing the damping settings will introduce more resistance to the motion of the cloth particles. So when you increase damping, it will dissipate energy faster. So the cloth will look like it won't react so much when external forces are being applied to it. External acceleration allows you to apply a constant force in a specific direction to the entire cloth, and random acceleration introduces random accelerations to individual cloth particles. It adds a random force to each particle, creating a turbulent effect. So the external and random simulation are usually used to create like a wind effect. Yeah. And the roll velocity and acceleration scale refers to how much roll space related objects or forces will affect the cloth in terms of its movement and acceleration respectively. Next is you are able to constrain specific vertices of the cloth. So the max distance limits how far cloth particles can move from their original position. The minimum distance restricts the minimum distance between the cloth particles. So in this picture here, I've constrained the particles on the top, so it's as if like the cloth is like hanging, it's like suspended by the pole. Now self collision settings. So the distance determines the proximity at which cloth particles are considered to be in contact with each other. So a smaller self collision settings makes the cloth more sensitive to self collision, so it will repel each other when it's too close. Stiffness property controls how strongly the cloth particles react to self collision. So if particles are in contact with each other, how strongly will it react? Is it gonna move away a lot or very little? And it depends on you. How do the cloth updates based on forces? So there are some examples of external forces acting on the cloth is like gravity, wind. So it will update the cloth by updating its particles velocity based on the applied force. So specific particles will be affected. Our collision detection and response. So the cloth it consists of a grid of particles that make up the cloth. So these particles interact with the colliders in the scene. So what you do is you drag specific colliders of objects that you want the cloth to react with, and once you do that in the picture over here, and the cloth will then react with that particular object realistically. So if let's say the object is applying force to specific particles on the cloth, those particles on the cloth will react realistically, so it will simulate a very realistic cloth behavior. There are also only three types of colliders that can react with a cloth: a sphere, a capsule, and a conical capsule collider. A conical capsule collider is when you attach two colliders of different objects into the same element as shown here. And the reason why Uni can react with three different types of colliders is because of to boost performance, since Unity's cloth component is mainly used for character clothing. Okay, now I'm going to talk about the cloth mesh setup. So the cloth component works with the skin mesh renderer to provide a physics-based solution for simulating fabrics. It's usually specifically designed for character clothing and only works with the skin mesh renderer. If the entire bounding value is outside the view of any active camera, the Unity will not render the mesh to optimize its game performance. So personally, we used material asset from Unity Store. It's a free carpet fabric looking material that includes both diffuse and normal maps. We also use a double shader asset from Unity's store so that it can render both sides of the plane object to simulate a cloth, since a cloth also has two sides, two faces. Now this is a way to optimize the cloth. So first is lower the settings in the skin mesh renderer. So as you can see over here, there are actually 4 options. One is auto, 1 bone, 2 bone, 4 bone, and lowering the amount of bones per vertex give performance. So what are bones? They are basically invisible objects inside a skin mesh that affect the way the mesh is deformed during animation. So bones are like joined together to form a skeleton, and rotating joints of the skeleton will make it move. So if you attach more bones per vertex, it will give even more accurate cloth physics, but it will also sacrifice your game performance. So by reducing this to, let's say, maybe 1 or just 2 bones, or leave it as auto instead of 4, it may be a bit less accurate in terms of its physics simulation, but it will perform much better during runtime. So what are the common challenges and solutions? So first is objects being visible through game objects. So this is the website that I found that actually solved this particular issue, which is just to increase the size of the object collider so that it's actually pushing the cloth a bit upwards so that the object will not be visible through the cloth. The other problem is jittery of cloth at high speeds. Now this problem arose when we tried to create a cape. So we attach a cape to a player, and when the player was moving too quickly, the cloth was very jittery. So all we did is went to the cloth component and decreased the roll, acceleration, and velocity settings, and we also increased damping. Yep. So this is the first cloth implementation that we did. This is firstly is a deformation of cloth due to an object passing through it in the first picture. So it just demonstrates bending and stretching physics, and how the cloth will react depending on the force applied by that particular object, whether it's going through it quickly, jumping through it, so on and so forth. Next example is cloth hanging on the pole, and it affected by gravity, and it basically demonstrates self-collision because during runtime the cloth will drop and smack itself, and it won't actually pass through due to the self-collision settings. Now the second implementation is first is the cape. So it demonstrates how the cloth actually works on the character like a clothing, and how the cloth reacts when the player moves forward and even collides with the cape itself. Second example is the cloth used as a hammock. So we suspended the cloth using constraints, and actually shows how the cloth will react, due to gravity. Yeah. Now the third implementation is a wind. So all we did is we just added random acceleration and external acceleration to simulate wind, and there's also a script to remove and add the random acceleration. And yeah, so in summary, Unity's cloth component is a very powerful tool for simulating realistic cloth physics. With careful configuration and understanding of its properties, developers can create an immersive and dynamic cloth effects. And what was covered is cloth component properties, collision detection and response, performance optimization, challenge and solution, and of course our tree implementation. And that is all for my part.
Hello, my name is Dixon. I am recording for my GMAPS presentation. The topic I'll be covering over is case studies for cloth simulation and cloth mechanics. Games that use cloth mechanics. I have found that many games uses cloth mechanic to have a realistic look to their game. These games include Assassin's Creed, Far Cry 4, Horizon Zero Dawn. In Assassin's Creed, the player character wears capes, and these capes uses cloth simulation in order to simulate the movements of the cloth whenever the player character move about. This game runs on an engine called Unreal Engine, which is created by Ubisoft, the same creator behind Assassin's Creed. because Ubisoft created Assassin's Creed using their own game engine, they are able to use the engine's enhancement in graphic physics and AI within the game development, and as such, Assassin's Creed is able to make their clove mechanic by using physics-based simulation that should be available within their own game engine. As such, the way that they tackled the common problem in clove simulation was that they used their own game engine, allowing for them to do finer adjustments. The next game, Far Cry 4, within the game, many characters wear long cloaks and some wear scarves. And all of these require clove simulation because these clothes requires movement whenever the player character moves, or even just the NPCs move. Far Cry 4 uses NVIDIA's physics for clove simulation in their game, and this engine allowed them to get a realistic physics effect and simulation on their clove simulations. This results in a more lifelike movement for the fabrics and clothes within the game. Lastly, Horizon Zero Dawn. In Horizon Zero Dawn, the character you play as has many fur clothes around her waist, which will shake as the player moves the character. The creator of Horizon Zero Dawn also used their own game engine called Decima Engine, which has its own custom physics engine for their clove simulation. It is also said that this clove simulation technology within the Decima engine was designed to provide a realistic clove behavior. As such, similar to Assassin's Creed, the creator of Horizon Zero Dawn solved the common problem by using their own engine, thus allowing them to more fine-tune their clove simulation. Now, to further elaborate on Horizon Zero Dawn's clove mechanic, Decima Engine, the engine which is used to make the game, is built for sophisticated clove simulation capabilities. As such, it's capable of having multiple commonly used techniques within the engine, such as being able to perform physics-based approach by using the model physical property to simulate the behavior of the clove materials. And the game engine would definitely also have a mass spring system, as well as constraint and forces, allowing for the cloves to maintain its shape and preventing unrealistic stretching. They would also have collision detection in order to make sure the cloves do not clip through objects, as well as a user-controlled parameter which allows for the game designer to adjust the parameter, allowing for more fine-tuning. That was it for case study. Now I'll be showing the references for my group. Here's the here's the references for the theories. Here are the references for Unity implementation. And lastly, this is the references for case study, which is mine. Thank you.
Hello, this is Donovan, and I'm going to talk about the implementations that I've done regarding Unity's cloth component. So first implementation, as you can see here, is a player that is made with a capsule game object with the capsule collider, and I just have a simple movement script so that this player game object can move around and jump as well. So I use a capsule collider game object because the cloth component only collides with the capsule collider and sphere collider. And as for the cape, I have set it so that the constraint is at the first two first two rows, because this is to mimic a cape that's attached to the player. And as for the collision part, so as you can see, there are many particles. So the collision part, I played around with values here and there, and I found the perfect value, which is 0.08, so that the cloth does not start jittering when the value is too high, or the cloth starts intersecting itself if the value is too low. And stiffness here is just to make it so that when it collides, when it has self-collision, it's not too flowy in that sense. So likewise with stretching and bending stiffness, I wanted it so that it can still bend and it can still stretch. So I think this is based on personal preference, so I'm just gonna play around the values here. Damping here is to make it so that it's not too flowy in the sense. So if I can show you right now, so before there was damping, before damping was set up, originally the value was 0. The cloth will, let's say if I were to jump, okay, right now the cloth is not too reactive. Previously damping was set to 0, and the cloth, even when I do a simple jump like that, the cloth will start to have too much reaction, which to me I don't think it's very realistic. So I just set a little bit of damping, and I added some acceleration, random acceleration, and an external one on X value, just to show a little bit of more flowing. And that's more or less about it. All I have to do, before that it did not work. I was wondering why the cape was not attached to the player, but after setting up the constraint at the first two rows, I was thinking, why not just attach this game object, the cape game object, to the player, and afterwards it works fine. So that's more or less about it. And so moving on to the second Unity implementation, which is the hammock over here. So I went online and searched for a few tree assets. Over here, the palm tree. And similarly to the cape over here, the process is more or less about the same. So I just set up the constraints on the corner, these 3 red dots over here, on the tree, because I want to show that the hammock is hanging from the tree itself, rather than setting up throughout the whole row and showing that the hammock is hanging in the air, which is not very realistic. So as for the self-collision of the hammock, I set it to 0.3 to, hold up, where is it? Over here. The distance between each particle as 0.3, as I just find that it's the perfect amount. And likewise, self-collision stiffness is set to 1 here as well. Bending here, I decided to not have any bending because I don't think it's really necessary, as I'm just creating a hammock. And I added a few acceleration to show that the cloth is moving, make it more realistic. And I added a collider afterwards, so that this player here can jump on top towards it, and so that it can land to show that the hammock is working. So let me simulate this. So I'll jump on top of it, and boom, there's a hammock. And as you can see from the bottom, you can see that the player is actually resting on the hammock itself. And let's say if the player were to just run through the hammock, right, you can see that. Okay, maybe in the middle over here, yeah, you can see the cloth is still colliding with the capsule. This is because the cloth just registered the capsule collider. And that's more or less my implementation. So thank you for your time and your kind attention.
is Zheng Kuang, and I'm going to present my Unity implementation. So I have two implementation. So I'm going to talk about the first one, which is it's the cloth on a metal pole. So it's basically this Singapore flag on a metal pole, and the main thing I want to demonstrate is actually how the cloth will be affected by gravity and the self-collision. So these are just some of the settings. I've set the stretching stiffness to 1 because I do not want the cloth to stretch at all. I want it to be like a very robust flag. And I set the bending stiffness to half, as during runtime, when the game runs, when the cloth actually drops, right, when it collides with each other, I still want the cloth to bend slightly so that it won't look so stiff. It will look a bit more realistic. I don't have any external acceleration, random acceleration, because I'm not gonna simulate wind, and I also do not have any damping because I want the cloth to react normally. So just to show you, I've constrained the middle particles so that it's as if like the cloth is hanging on the pole, and also the self collision. Yeah, the distance I set to 0.2. This is because of the size of the flag. It's not extremely big, but I wanted the particles to be more like the distance between each particles to be big enough in such a way that I'm ensuring that there'll be no scenario where the cloth intersects with each other, and the stiffness is, I've set to 1 cause if let's say the particles do collide, I want it to repel. Yeah, I just want it to repel. I do not want it to collide at all. Yeah, okay. Now my next implementation is the cloth that is attached to a tree pole. So I have 2 trees over here. This is just normal assets, and I have actually a tree pole over here. And I have a cloth attached to the pole. So I set the stretching stiffness to 1 again because I do not want the cloth to like stretch at all, because in this implementation I'm going to use a ball like an object, and I'm gonna run through the cloth. So I'm gonna show you how the cloth is able to deform realistically through the shape of the ball, whether the ball is jumping, the movement speed of the ball, and so on and so forth. So yeah, I've set the bending stiffness to 0.8, which is a bit more than the flex, because there's a lot of there's going to be a lot of forces acting on the cloth at once, because I'm able to move the ball in front, back, and it's just gonna make the cloth react a lot. So I made the bending stiffness to 0.8 because anything lower than that, the cloth is gonna start bending a bit too much. Yeah. I also have a bit of random acceleration. Just set it a very low value just to simulate a little bit of wind, but it's not really that important. And the constraint, I've only constrained the first 2 rows, so that it's as if it's like constrained to the top of the pole. And also I have set the self collision distance to 0.4. This is also with respect to the size of the cloth. So this cloth is a little bit bigger than the flag, so set the distance to 0.4. So such in a way that the cloth will not there won't be a scenario where the cloth will intersect each other, since I set the distance to 0.4, so that's like the max distance the particles can come in contact with each other before the collision stiffness will repel the particles apart, preventing the intersection problem. Oh yes, I forgot to mention, I've also added the 3-pole capsule collider to be able to wrap the cloth. So this is the 3-pole. So if let's say a scenario where the, the player is able to jump very high and is able to push the cloth such in a way that it falls over the pole, it also is able to react with the pole, and of course it's also be able to react with the ball over here. And I forgot to mention for this cloth, the flag cloth, I have added the cylinder here, the pole here, so that it can deform to the shape of the pole, and just in case I've also added the other two poles that's supporting the top pole. And let me just run to show you firstly the flag first. So I'll just give you a moment. Okay, as you can see, the cloth actually comes down like this, and it will actually smack each other. And now the cloth is still moving, is because as I showed you just now, I do not have any damping settings, so there's no scenario where the energy will dissipate quickly, and you can see it start to slow down a bit more now. The energy is caused by the fact that when the game started, the cloth came down and collided with each other, and the stiffness is set to 1, so there's going to be a bit of a force. Now as you can see, for the cloth, the wind is affecting the cloth over here, as per normal. And let me just take the ball, so I'm able to move the ball, and I'm able to collide with the cloth. I'm basically applying forces to the specific particles of the cloth, so the cloth will deform realistically. So if I just move closer over here, you can see that if it comes to rest, it actually deforms to the shape of the ball. It also has a self collision setting, so if let's say the cloth do collide with each other, something like this, a little bit, it hits the pole or hits itself, it's gonna react realistically as well. And you can see, when the ball manages to push the cloth over the pole, it's going to react realistically as well, because I've dragged the 3 poles collider onto the cloth component, so it react. And if let's just say a scenario where I increase the movement speed by a lot, okay, that's too much, 8, and I increase the jumping height to twice the height, it's able to jump very high, and can see that the cloth actually still reacts realistically despite the ball's speed and jump height being extremely almost doubled. So what does this mean is, well, more force will be applied to the cloth, but the cloth will not break. It will still react realistically, even though it's a bit it's a lot of force. And this is the scenario I was talking about previously. If the ball manages to put a cloth over the pole, nothing will happen, the game won't break, the cloth will still react realistically, it come down, and that's all I have to show for my implementation.
Hello, this is Dixon. I am recording for my GMAPS cloth implementation. So, I would be demonstrating my scene, which would talk about the wind, which would show how to simulate wind mechanics using the cloth component. So in order to simulate wind, you would have to change the external acceleration of the cloth component. By changing the external component, like what I'm doing right here, I can simulate wind. Like so. Changing these value changes the direction that the wind is blowing from. Y would be blowing from upwards, Y minus would be blowing from downward, X is blowing from this direction, and Z is blowing from this direction. So, and the way to and I've coded a function called wind script, which allows you to control the external acceleration of the cloth material using a script. So I've coded it such that if I press space, the wind will be blowing from the x coordinate, such as press this. You can see I have set this is the modified acceleration. The previous one is the new acceleration. So the modified acceleration would be the acceleration that this function would set the cloth object into, whereas the new acceleration would be when the space button is not pressed. So as you can see, the external acceleration, when I press the space button, the z becomes 10, and when I let go of it, it becomes back to 0. So that's how you simulate wind. Another way to simulate wind would be to change the random acceleration of the object. By using the random acceleration option instead of manually having external acceleration, the game the external acceleration of the object can be randomized, thus simulating how wind behaves in real life more properly, so that for example, it won't be continuously blowing, and instead it'll just blowing some of the time. Anyways, that is all that I have for my video explaining my scene. Thank you.